Well, today is March 14th. What's the significance of that day? Well, it's Albert Einstein's birthday. But that's not why I'm talking to you. I want to talk more about his work. In 1905, he published 4 groundbreaking papers, all in the one year, mind you. 1905 was referred to as his annus mirabilis, or his miracle year. And 3 of those papers had a fundamental, groundbreaking effect on not only physics, but our society today. The first paper was the photoelectric effect. Now, in essence, that paper helps us understand how solar panels work. That light is not acting as a wave, but as particles, or we now call them photons. But it opened up the physics of what we refer to as the quantum physics or the quantum mechanics era, and it completely transformed our understanding of the reality of nature. But it also had impact on you and I in terms of technologies. In fact, 50% of all economic activity is ultimately based on technologies that have their origins in the quantum physics that Einstein initiated. Now, his second paper on the special theory of relativity basically changed our way that we view time. Time isn't something that's absolute. No, time is relative. It basically means what we measure as time is different depending on what the observer is doing. And so we have these ideas of time dilation, that some things can age differently at a different rate because they are moving relative to something else. Now, that later led to his paper on general theory of relativity, which had the wacky idea that gravity is not a force but a distortion of space-time, and as a result not only helps us to understand how GPS satellites work because they rely on that principle, but it helps us understand the origins of the universe with the Big Bang, and also the progress of how the universe is developing. Now, his third paper, which is probably his most famous and shortest paper, in fact, was E equals mc squared. Now, you've heard of that. It's the most famous equation in science, and in essence says that energy and matter are really just the same thing, and you can convert one to the other. Now, that helps us understand the origins of the universe, where energy converts into matter, and it also helps us understand our technologies such as nuclear reactors and, of course, nuclear weapons, where matter can turn into energy. But it's also, for example, used in the concept of radiopharmaceuticals, life-saving drugs to treat and diagnose cancers, where again the understanding of E equals mc squared is fundamental to that process. It would make sense that if so much of physics today, so much of our society is based on Einstein, that we would learn it from an early age. Well, that's actually not true. It's sort of ironic. Often schools leave Einstein Physics way until the end of their schooling, year 11 or 12 at best, and most of the time it's university that it's placed at. Now, why? Well, it's thought to be as too challenging, too difficult, but there are many who argue that's just not the case. And that leads us really to the purpose of this video. Magdalena Kersting and David Blair wrote a book teaching Einsteinian physics in schools, where they argue that Einsteinian physics should be front and center in the science classroom. Now, Magdalena is an educational researcher and physics educator based at the University of Oslo, Norway, and has published numerous papers on effective physics education. Now, David is an experimental physicist based at the Western Australian University, and David's pioneering work was underpinned the precision of LIGO to allow for the detection of gravitational waves, which were predicted by Einstein, and they were detected in 2015. And he was instrumental in the establishment of the Australian International Gravitational Research Centre. Now, both have a passion for Einsteinian physics education, and they love to see it taught right across the school curriculum. Now, what's their thesis? Not only can Einsteinian physics be taught in the school at a conceptual level, it actually should be taught much broader across their whole schooling. And their argument is this: Einsteinian physics not only gives them a more accurate model of how the universe works, but it allows for teaching concepts in an innovative and creative way that engages them and helps them better understand the world that they live in. Now, stay tuned. Later in the video, I have a chat with Magdalena and David about their work. Now, this book is not just one treatise or argument for teaching Einsteinian physics in the classroom. It's in essence developed divided up into 3 sections. The first section, they lay the groundwork for the rationale of teaching Einsteinian physics in the classroom, and they include why relativity was left out in the school curriculums in the 1940s and the 1950s. Now, in the next section, which I think is the crux of the book, they proceed to introduce each of the physics concepts involved with Einsteinian physics: special relativity, general relativity, and quantum physics, providing a primer or a view for the reader to understand the concepts at a conceptual level. And they introduce a variety of activities and lesson plans to help them teach those concepts at an appropriate level for the classroom, be that the primary classroom or the secondary classroom. Now, throughout it all, they discuss the important principles of science education, that is, how science works and the language of science. Finally, they examine case studies from around the world where Einsteinian physics has been integrated into the school curricula. Now, this is, I think, very important as it highlights of what David and Magdalena argue. It's not based on academic research alone, but by classroom-tested pedagogy, and it's done in a variety of country contexts. Now, although this book has their names on the cover, it's more accurate to say that they edited the book. Though they contribute obviously a significant portion of the book, there's quite a number of contributions, in fact 30 to be precise, by experts in their field, whether it is science or educational experts. You don't need to read this book in order. You can jump straight to the relevant chapter that interests you. Each chapter provides a brief summary of what's intended and what they cover and whom it's basically intended for. I really like the fact that it includes a conclusion that summarizes the key points and then also provides resources for further reading and for other references. Are they convincing in their case? I have to admit that prior to reading the book, I was of the view that much of Einstein's physics was conceptually challenging and therefore too challenging for younger students, and therefore more appropriate to be taught at the last years of high school or beyond. Now, I have to say this book has modified my view. Now, I've been persuaded that there are many physics concepts that Einstein introduced that can be covered in the classroom at an appropriate level relating to their own experiences and can be introduced without cognitive overload. By introducing better scientific terminology, by teaching them how models in science are developed, students will be better equipped to engage in science for the later years. And I think the end result is not that students have a thorough knowledge of Einsteinian physics. I think there's always more to learn, but the ultimate goal is to engage the students in science. Now, with that, of course, there are some caveats. We need to ensure what we convey to our students is appropriate to their cognitive level. We're not going to be teaching Einstein field theory to Year 3 students. So if we are to introduce new concepts to the students, first and foremost, we have to ask the question, is it something that they can understand? And the second question, can I express it in ways to help them understand? Now, the authors recognize this, and the activities are age appropriate and language terminology is introduced that younger learners can understand. Now, a really good example is the way they talk about light, that it has bullet-like behavior and wavy-like properties. Now, second, this is not to say that Einstein physics is easy at a conceptual level. It often isn't, as much goes counter to what our common sense or our preconceived notions tell us. And as I read the book, I had to read carefully and think. And so too your students also will need to think if you're going to introduce Einstein physics concepts. But that's really not a bad thing, is it? You're encouraging your students to develop critical thinking skills, which I think is all important for our students. And the reality is that much of classical physics is also equally challenging. In fact, I still get Year 10 students who struggle with Newton's third law and think that gravity stops as soon as you leave the atmosphere. Now, there are some other constraints. The author would like to see more Einstein physics in the curriculum, but the question is there an expense? Now, much of the curriculum that we teach, depending on what system you're working in, is quite content dense. Where are you going to find the time to teach some of these concepts? Where are we going to introduce new concepts? Does something have to give? Now, personally, I think it is possible to teach these things, but we have to teach smarter. Rather than replacing, teachers modify how they teach certain concepts. So it can be introduced where you teach light in year 9 or forces in year 7, and include activities that introduce these concepts, not to replace, but to introduce another model. That leads to another constraint. Often it is the physics teachers who have a good understanding of the physics of Einstein and therefore can help students to understand them, but that's really not the case. Many teachers are not trained physics teachers, and this is even more true for primary schools where teachers don't get a lot of science training. How effective are those teachers going to be if physics is not their expertise? Teachers will only be convinced to implement the concepts if they themselves are confident of their own understanding of the concepts. So the question is, how do we address this lack of expertise? This naturally segues to my next point. So who should read this book? First of all, I think it's a valuable resource for teachers of science, especially those in high school, to have on their shelf. And I'm not just referring to physics teachers. I think any teacher who's passionate about improving the scientific literacy of their students and helping them understand and develop an intuition for science should have this as a reference point. Now, apart from deepening an understanding of physics concepts as well as a historical development of the physics concepts, I think this book teaches a variety of interesting and engaging activities that can be implemented in the classroom. Who would have thought that you could bring out your Nerf guns and ping pong balls to try to teach the photoelectric effect? Now, as I said before, this book can be referred to multiple times as a reference source, so you don't need to start from the page 1. Now, secondly, I think this book is an excellent book to provide any person who's interested in Einsteinian physics, because it's accessible in a conceptual way. So although the target audience are science teachers and not necessarily the general public, I think anyone with a good understanding of high school physics and science in general should be able to deepen their understanding of the work of Einstein. Now, the descriptions and explanations provided in topics such as photoelectric effects and general relativity and other concepts of modern physics are predominantly conceptual. There is some mathematical analysis provided, but it is kept in a minimum, and where it is provided, and that is mathematics, it's often placed in boxes so that the reader can choose to read them or just continue to move on. This book isn't going to radically skill up all teachers to Einsteinian physics, and nor is that its aim. But even if it helps a teacher implement a small change in the way that they teach, students are going to benefit from having a better understanding of the world that they live in and a better understanding of how science works. Now, I had a chat to speak to Magdalena and David about their work. Well, welcome David, welcome Magdalena. If you wanted a teacher to read your book, what would be the nutshell of this is why you should read it?
It gives you a comprehensive introduction to Einsteinian physics education and both the Einsteinian physics and the education. So if you would like to learn more about Einsteinian physics concepts, you find a proper introduction and a glossary to those concepts. If you're interested in the education part and instructional activities, how do students learn, why and how are they being motivated, then you find that in the book too. So it's really Einsteinian physics education, emphasis both on the physics and the education.
Was there some seminal moment that for either of you is like, oh, this is really important?
Well, for me, it was giving public lectures to all sorts of different groups, and but particularly to bright, intelligent, educated people, and you would get up and talk to them, and they would say, "Wow, you must be a genius to understand this stuff." And I knew that I was not a genius. I knew that there was nothing actually very complicated about it, but it was that perception. And then when I first started trying to teach the same things to year 6 kids, which was done with certain trepidation, and I tried to tell them exactly the same story I was telling these adults, it was one thing was astonishing, and that was the kids were not astonished at all. They just took it in their stride. It was easy for them. They loved its explanatory power. They loved some of the slightly difficult and weird aspects of it too. That was made it the most interesting part. So it was that fantastic receptiveness of young people to those ideas that told me that, we really need to do this.
Yeah, and maybe building on that, I love working with middle school students because they still have an interest, like they are so fascinated by Einsteinian physics. And it's exactly this age group that often loses an interest in science and physics. And it's a tragedy because like modern physics, like what could be more exciting and more interesting? And we all have this kind of deep curiosity about our place in the universe, where we come from and what's out there. And Einsteinian physics gives answers. Yet in school, students just like they are so, I don't know, like they just completely lose interest because physics education, when I went to school, like my physics classes were absolutely boring. Like, why would I want to learn about 19th century, like pendulum movement? I don't know, like it was just boring, right? And I think for me, being able to work with middle school students and seeing how you really get them excited and how a whole new world opens up for them and they see, oh, wow, that's physics. I hadn't realized that physics was that interesting. That might be something for me. So I think just showing them that physics is more than just this outdated textbook knowledge.
Well, last year for National Science Week, I was giving a talk to a primary school. I had 600 kids sitting cross-legged on the floor in front of me. And I asked them, put your hand up if you've heard of black holes. And 80% of the kids put their hands up. It was just a forest of hands. They'd all heard of black holes. But could their teachers tell them anything about black holes? No. And this is just an example of the fact that kids are, through the media, are in touch with all sorts of snippets of information about modern physics. Today, they're hearing about the James Webb Telescope and looking back to the first stars in the universe. All these things are there, and then they go to school and they get this 19th century science.
You say that 19th century physics is boring. Maybe the issue is not that the material is boring, but the way that it is actually disseminated. So, for example, I think one of the things that you said about Einstein physics, the idea is to connect them to the real world. You know, teaching some aspects of Newtonian physics or whether it's heat can actually be still very interesting, but it needs to be connected to their life to see how it applies.
But if you ask what are the things in kids' lives today that fascinate them, that they know are important, that, you know, they would like to hear about, not only things like black holes in the universe, but things like climate change. They are told, you know, too much CO2 in the atmosphere makes it get hotter. And they're told that somehow that CO2 absorbs heat and makes a blanket. But they also drink soft drink in clear plastic bottles with CO2 gas on top of it, and you can see right through it. It's quite transparent. There is no explanation given to them as to why this happens. But the explanations are easy. Einsteinian physics has got fantastic explanatory power. Things are explained in a simple way that people can understand, and understanding is empowering. So 19th century physics talks about heat without mentioning atoms. That is, and which is how they teach heat in year 3. People decided you couldn't teach kids about atoms because they were conceptual. Well, in the 1930s, perhaps they were conceptual, but today we have machines that used Einsteinian physics, use things like quantum tunneling to enable you to see atoms. And now we can make movies with single atoms. Things that were abstract are now part of observational reality. We shouldn't exclude children from this knowledge.
I can maybe quickly add that, of course, we all recognize the value of classical physics. And one of our arguments is that we shouldn't start with the classical physics, but that we start with Einsteinian physics and then connecting it back to the lives of students. Because as David just said, understanding is empowering, and we want to empower the students, showing them this is, or like, giving them a vocabulary with which they can describe and understand the world, and then connecting it back to their everyday lives. See, Einstein's space-time explanation, if we just look at our planet, where gravity is weak or the gravitational field is weak, we have these simplifications, and equations actually get much easier. So I don't think that we are arguing against classical physics per se, but it's about how we want to introduce students to these concepts. And if we start with Einsteinian physics, if we start with our current best understanding, we can show them what they can explain and how they can go back to classical ideas.
In relation to that, also, it's very, very useful to be able to show how ideas developed, and to show that history of ideas, when we can then say we know better and better what the universe is made of and what it's like. We need to be able to show students that there was a process of discovery, and this has been going on and on. It's a most exciting story. If you look at that story of discovery, look at Galileo, look at Copernicus, look at Newton, how these ideas evolved, where those ideas were right, where they were wrong, how this changed our way of thinking, and how we got to where we are today.
The curriculum already is quite crowded, at least in a lot of Australian jurisdictions. How do we address the challenge of a curriculum in most jurisdictions being already quite full?
No, we've thought about that a lot, and we particularly thought about it as we've been developing our Einstein First curriculum. I can give you several sort of examples of it. One is, for example, the way we teach gravity with a lycra sheet, where all of Newtonian gravity is there in the most beautiful way in this analogy, not a perfect analogy, but one that still has got great explanatory power. Newtonian physics is there, but general relativity is there as well. So it's all there with a much more explanatory power than simply writing down Newton's law of gravity and saying that the planets attract and they go in ellipses, because you see it, you can do experiments with it, you can observe all the interesting things that happen. So there's one case, but there's another thing that's really important, and that is unifying concepts that have come out of physics. All sorts of concepts exist that are given different names and made out to be something quite different. For example, you've heard of binding energy. And binding energy is what they talk about when they talk about nuclear reactions. But binding energy is, what holds you on the surface of the Earth. There's gravitational binding energy. Two magnets hold each other by binding energy. There's one, DNA molecules hold themselves together by binding energy. Cells hold themselves together by binding energy. So there's a single concept. And if you are willing to do away with some of the language that creates a sense that there are lots of different processes, and go down to the simple basic concept behind it all, you've suddenly been able to encompass a whole lot of topics by learning just one idea. In almost all cases, it comes to changing the elaborations on the curriculum, not the curriculum itself. We've created this full Einstein First curriculum that goes from year 3 to year 10. And each year follows the spirit of the ACARA curriculum, except for a few cases where the curriculum is actually asking teachers to say things that are wrong. We don't really change the curriculum. We simply mold it to be in line with our best understanding of the universe.
It really requires not so much as of starting a fresh page, but for the teacher to actually use a better language, a better scientific Einsteinian literacy. Instead of talking about gravity is a force, well, why don't you say, one way we can describe gravity is a force, and then you can talk about, the idea of, that there is a better understanding. So you're introducing the language of Einstein by also recognizing that everything we do is actually a model with its limitations and its strengths and so forth. The idea of contact, non-contact forces, we can describe them as contact forces, but in reality, it's actually not.
I love that you introduced the notion of Einsteinian literacy, because I think that captures it perfectly. And part of Einsteinian literacy, as you mentioned, is just being aware of the nature of science, the way our knowledge expands and progresses, and also the way we use models in different settings, and discussing the usefulness of models, but also the limitations is part of Einsteinian literacy. So I think I'm just going to use this term from now on because I really like it.
If we're doing this in the classroom, we want teachers to take that up away from year 3, year 4, right up to year 12. A lot of teachers are, I think, ill-equipped to teach those concepts. I've seen experience in my teaching career of a teacher who isn't science trained and asked to teach a science lesson. I've seen teachers who are biology trained, but they're thrown to cover a physics class. The risk is they'll teach concepts in a way that's actually incorrect. How do we address this? How do we get teachers on board to make these paradigm shifts in the classroom?
Last week we gave a course called Teaching Einsteinian Physics in Schools to a group of primary school teachers. We've been doing lots of these things. I think we've nailed it, this particular problem. If I say to a teacher, Einstein's theory of gravity, is a theory about space being curved, and I'm going to teach you about that, their brains freeze. They are all ready to switch off before you even begin. But if you say, we're going to roll some balls around on a sheet of lycra and we're going to observe what happens, and then we're going to interpret it. So this is what I call the activity first approach, where you put an activity or a model forward and you say, let's play with this model. Then you say, now what does this model signify? Well, this curved piece of lycra is actually a two-dimensional representation of space, and it was curved, and the geometry you did on it was different from the geometry you normally experience. And so you bring them into it through the activity, which is painless and fun, and then you uncover the concept that is related to it.
That, of course, paradigmatic changes do not happen overnight. Mm-hmm. It's not that we can just like this expect every teacher to be Einsteinian literate and to be able to teach this right away. So there's a lot of work we need to put into teacher training, and I think the longer I'm working with teachers and the longer I do research in Einsteinian physics education, the more passionate I become about teacher professional development courses and really guiding teachers and working with teachers. And it's not something that's going to happen overnight, but it's just something step by step, doing these courses like David's team. And we have to think just like 10, 20 years from now, like the students that have been educated, like in Western Australia, in 10 years from now, and 15 years from now, they'll be the next teachers, right? For them, it won't be as scary, or they've grown up with an Einsteinian vocabulary of the world. So I think it's just like our transition phase where we all have been like the way we grew up was in this Newtonian rigid framework of space and time. And then it's just, of course, it seems mind-blowing, and we need to, we are maybe a little bit scared to just revise our worldview. But 10, 15, 20 years from now, students or like our future teachers will be better equipped. So it's something that we strive towards, and it's not going to change overnight, but we can work on it day by day, teacher by teacher.
What advice would you give to a teacher who says, David, Magdalena, I want to incorporate more Einsteinian physics in the classroom?
Read our book. Read our book. Come to our training courses. Go to find some professional development courses. Read some of the papers that shows how easy it is to teach these modern ideas.
And for those teachers who are not able to attend a professional development course, just try to sneak in Einsteinian physics. There are a lot of physics concepts in the curriculum that can be linked to Einsteinian physics. Let's just say every physics curriculum has a unit on waves. Why not include gravitational waves, right? And for almost every topic you have, you can include or you can sneak in the Einsteinian concepts. So it doesn't even need to be like, you don't need to be working within a modern physics curriculum. Just start where you are. Try to sneak in a little bit of vocabulary. Share YouTube videos with your students, right, Paul? You've created an amazing hub of videos, many of them touching up on Einsteinian physics topics. So I think just be sneaky about it and just feed students a little bit of Einsteinian physics here and there.
Well, thank you, David and Magdalena, for your time.
Absolutely. Thank you, Paul.
Thanks.
Well, I hope that has given you an insight of this book and encouragement to have a read and take it on board. I will put a link in the description below as to where you can buy it. Please like, share and subscribe to this video, and if you value this work, please consider supporting me by buying me a coffee, and put a comment down below if you want and I want to add to the discussion. My name is Paul from Physics High. Take care and bye for now.